Let me introduce myself. I'm Faridul Islam. I'm a physician here, but I'm curious about philosophy and science in general because, like yourself, curiosity is a basic human instinct, right?
Yeah.
So, when I see your discussion, I feel like you have something different to say than other philosophers, especially about foundations of physics, foundations of philosophy in general. So I just wanted to talk with you. So let me introduce you a little bit because this is our first meeting. You are Professor Tim Maudlin, professor of New York University at Philosophy Department. And also you're a founder and director of John Bell Institute of Foundations of Physics, right?
That's right.
Okay. So how do you start this institute and how long ago?
It was about 4 years ago, 5 years ago. The reason I started it is pretty simple. It's just because foundations of physics, although it's a field in theory, isn't really accepted as one in academia. There's no place for it. And so every summer I would be going around to summer schools, to conferences, because in the summer, because it's not that many people do it, and they do it, they're all spread all over the world. And some students are interested in it, but they're also spread all over, and they tend not to have people around them who do it. So there's a lot of summer schools where students get introduced and conferences. But I just thought it would be better if there was a physical location that was dedicated to it, and with a faculty and with a bunch of fellows, just to promote interaction, because it's a very diverse, it needs a diverse set of skills to do well. So by charter, I wrote the charter, and by charter, there are 6 members on the Board of Governors. 2 of them are physicists, 2 of them are mathematicians, and 2 of them are philosophers, because you really need all of those skills. And the best thing is to have people from all the different disciplines together talking to each other. So I just thought this would be a good way to try and promote that.
And also one point to notice, I think most of the university graduate programs in physics or in philosophy, they don't touch those kind of foundational questions, right? I think that's why we need a separate entity so that those people who are interested, they can find you and they can
Right.
from the masters. Like,
yeah, and hopefully it's a step, a step in a direction. The main problem is, of course, in physics departments. So that is if a philosophy department has a philosopher of physics, then the students there can learn about it. What you would hope is that physics departments would at some point think, hey, maybe we should actually have someone who does this, and put courses on, just physics courses in foundations of physics. I can certainly testify there's a lot of interest in the students, in the physics students, because when I do philosophy of physics courses in the philosophy department here, I get a lot of physics students. And they often say, this is why I went into the field, to ask questions like this. So if we're lucky, slowly, and there's a few indications this is true, it'll migrate and have a bit of a home more in physics departments where it really should be.
yeah, that's actually great. And plus, we outsider who has general interest, we can also understand what you guys are talking about, because most of the time when you talk with the same discipline technicalities, it's very hard to follow because it's interdisciplinary. Outsider like us, we can appreciate what you are talking about. So I know I have a gut feelings, and based on your podcast that I listened, I think you have little bit of contrary and like view on like on quantum physics and also in relativity and also especially on nature of time.
Well, I should just mention the 3 topics you just mentioned: quantum mechanics, relativity, and then this and time. And then there's also this discrete space-time stuff I'm working on. They're very, very different. So, to say one has a contrarian view on quantum mechanics is a little odd, because there's no really no received view about it at all. It's not as if there's some account of what quantum mechanics indicates about the world that physicists, even physicists who specialize in it, would all agree to, and I'm like on the other side. It's rather just a complete free-for-all in terms of what the problems are and what the possible solutions to the problems are. Now, that goes all the way back in a certain way, even to Planck. I mean, Planck didn't exactly start quantum mechanics because what he was doing was so just an observation. He knew a result he wanted to get from observations. And the normal calculational techniques that they used in physics weren't giving him that result. And he realized that if he instead of treating especially energy in a kind of continuous way, if he just put down little discrete finite sized boxes of energy and counted in terms of those, and didn't let the size of those boxes get as small as he wanted, he got the result he wanted. Now, that doesn't, if you say it that way, that's just a piece of math. That's just a mathematical observation. People often say, oh, Planck postulated that energy is quantized. He really didn't even do that. He just noticed that a certain way of doing a calculation gave him a result that was in line with observations. In a way, and it's, again, you just shake your head, in a way, quantum mechanics really begins in 1905 with Albert Einstein, because he was looking at something called photoelectric effect and realized that he could explain the observations of photoelectric effect by really assuming energy only came in certain kinds of discrete packets. But even then, it wasn't clear to him exactly what was going on. And then you had a 20-year period, the so-called old quantum theory, when Bohr was suggesting, again, just taking this idea, well, maybe energy only comes in discrete quantities. If you apply that to a kind of planetary model of the atom, because how much energy an electron would have would depend on its orbit. If the energy only came in certain discrete units, then you couldn't have orbits of any size or any velocity. So you'd have to jump from one to another, right? You jump from one energy state to another. So that was the so-called old quantum theory that Bohr worked on, and has this kind of planetary model of the electron and so on. But again, it was just numerics. It wasn't really anything that gave an explanation in terms of what was really going on. And they were very worried about that. They said, well, wait, what is the electron doing in between these jumps, between these energy states? And how does it get from one to the other? And these were very natural questions. And then in 1925, Heisenberg and then Schrodinger invent the new quantum theory, which is what we now work with. Heisenberg, again, was so much just a piece of mathematics that it was called matrix mechanics. And matrices are just arrays of numbers, I mean, it's not a physical postulate, right? If you say, I'm going to use matrices, that's a mathematical comment. It's not a physical comment. And Heisenberg kind of invented this matrix mechanics. Again, why? Because nice results were dropping out. And then Schrodinger invented what's called wave mechanics. And people felt like with the wave mechanics, the mathematics was, again, the mathematics of waves, the same math that they were used to in dealing with waves, but the introduction of this thing we now call the wave function for a system.
Yeah, I think you mentioned about the wave function. Many physicists, I think, take wave function as a mathematical construct rather than a physical thing that you can measure. But I think you are in opinion that the wave function or field is not just mathematical construct, rather they might have some physical correlate or something.
Right, and that's the right way to put it. The wave function, in a way, by definition, is a mathematical thing, as I say, because it's a function, and functions are mathematical things. So the question is, okay, you've got this mathematical thing that Schrodinger introduces, and he introduces some rules about how to manipulate it and what the equations are for it, so-called Schrodinger equation. But that leaves quite open, what does this represent physically? I mean, what's going on in the physical world? It's easy enough. You can always introduce numbers, but you have to think about what they mean. And if you misunderstand what they mean, you'll get very confused. So if someone says, take a very simple example, someone says, oh, the average family has 2.3 children. You can say, okay, there's a number 2.3, but I don't understand. How can there be 2.3 children? How can and of course, no individual family can have 2.3 children, but the average, as it were, the average family can. It's not that hard to understand what's going on there, but there's certainly a step of explication. How is this piece of mathematics being used to represent what's going on? And so in the case of the wave function, every possible position on the meaning of it, as it were, the significance of it, has been suggested and defended. And at one end are people who don't think it represents anything physical. It actually just represents our degrees of belief. It represents something about what's in our head. I mean, a similar sort of thing. Suppose I tell you there's a 40% chance of rain this afternoon. We say, well, what is that? 40%. Okay, that's a number. What does that represent? Is that telling me something about the amount of moisture in the air? And someone might say, no. It's just to say that based on looking at the past, given these conditions, it rains about 40% of the time. And your expectation ought to be 40%. But out in the world, right now in the atmosphere, you won't find anything 40%. So in that case, you could say, yeah, there's a number there, but that number really represents how likely we think something is, or how likely you ought to think it is, not something in the physical world. And then there are people who say the wave function not only represents something in the physical world, it represents all there is in the physical world. My friend Shelley Goldstein sometimes says there are three possibilities for the wave function. Either it represents everything, or it represents something but not everything, or it doesn't represent anything. And all three have been taken. And so I would say most physicists either go with it doesn't represent anything physical, it's just a kind of calculational tool, or it represents everything physical. This view that it represents everything was the one that Einstein called regarding it as being complete. He introduced this term, is the wave function complete, in a paper that he did with Podolsky and Rosen in 1935, the so-called EPR paper. And the title of the paper is the quantum mechanical wave function of a system complete? And by complete, they meant somehow the wave function of a system represents all of its physical characteristics. And then there's this middle view that says, well, it does represent something physically real, but not everything. There's more. It's not complete. Now, so there are your three possibilities. I think the one that it doesn't represent anything is just, you can't defend it. It doesn't make it, you can't understand anything of what we've seen if you don't think there's something in the physical world that's being represented by the wave function.
Yeah, if it is completely mathematical construct without a physical counterpart, it should not predict the observations so nicely that we see. So the wave function has something to it rather than just like mathematical construct that has nothing to do with anything physical. So I also, general audience, like as a general person, I think the wave function might have something rather than just pure mathematical speculation.
And it's more than just that it makes good predictions, it's how those predictions are made. So again, let me go to a case probably everybody's heard about, the so-called two-slit experiment. So we start with something we do understand. If I have a beam of light, or even easier to understand, a water wave. So, and people hopefully did experiments like this maybe in school, where you have a water table and you have something vibrating at one end, and you get these nice plain water waves coming in, sort of like at the beach. Okay. And you understand, okay, the water wave is just the water has height and it's moving, and this thing comes, and then you can hit a barrier with two slits in it. And you can just see on this water table, okay, I get a little circular wave coming out of this slit, I get a circular wave coming out of that slit. They go forward, and where they meet, they interfere, which is just the height of the water at a certain point is the height of the water of the wave coming from one slit plus or minus, you add the two heights together from these two sources, and they can interfere constructively. If they're both positive, then they add up, and if they're both negative, they go down, and if one's positive and the other's negative, they can cancel out. So you get constructive and destructive interference. And then when you look at the screen, you see these bands, you see these interference bands. So you'll get a lot of activity here where there's constructive interference, and then none where there's destructive, and then a lot of activity again. So you have this characteristic precise pattern of interference bands that's associated with waves, and importantly, associated with the wave going through both slits, because you need two sources here. Now, what was discovered is that electrons do this. So for waves, it's perfectly clear what's going on. For water waves, you understand very well what's going on. But if you take electrons and throw them at a wall with two slits, or throw them at a crystal, and then look far beyond it, you also get this interference pattern. And the weird thing, the thing that really surprises people, is you get that pattern even when, as it were, you're throwing the electrons just one at a time. You can turn down the beam so low that you just get a dot, and then you wait a while and you get a dot, and you wait a while. And if you wait long enough, all of those dots form these interference bands. And there you can be very, very puzzled, because you say, wait, the wave, to form the interference, something has to go through both slits.
Exactly.
Right? Because the interference is of these two different pieces, but I'm only throwing one electron at a time. How does the electron go through both slits? I mean, how? And of course, in quantum mechanics, you associate a wave function with even a single electron, and that a wave function is, as it were, mathematically represented as spread out and interacting with both slits. And so the interference pattern, it's essentially impossible to understand how that interference pattern could form if the wave function didn't really represent something physical that's actually interacting with both slits.
Yeah. Is there any experiment that you know where electron, when faced with two slit, acts like a particle instead of waves? Is there any setup?
Well, people often say, oh, sometimes particles act like waves, and sometimes they act like waves. Sometimes electrons act like waves, and sometimes they act like particles. But that's just things often said. What this experiment indicates is that in one and the same experiment, it's acting like both. It's not that you're choosing between them. The particle-like behavior is because you just get these individual dots. If I'm using water waves, I never just get a dot. The entire wave goes through, some of it goes through the two slits, and then it finally ends up at the far side, an entire wave. You don't get these discrete events. So you do get those. That's certainly makes you think of particles. But when you sum up all these dots, they give you this interference, and that makes you think of waves. Now, John Bell, in one of his papers, says, in the incisive way that he says, for years, they were arguing particle or wave, right? What is an electron? Or maybe you make up a word like a wavicle or something like that. He said, why didn't it occur to them the obvious answer, particle and wave? Maybe the reason you have these two aspects of this behavior is that there is a particle and there is a wave.
Exactly.
And what the wave is doing is guiding the particle. That's the so-called pilot wave picture. Now, that's not a popular picture among physicists, but it's been around since 1927. It's been around from the very beginning by de Broglie. And it makes perfect sense of that experiment, right? And it does it in a very easy to understand way. Sorry, yeah.
You can predict the same results using the wave and particle, the pilot wave theory, that the traditional main theory
right.
so predicts identical, right?
It makes exactly the same predictions as standard non-relativistic quantum mechanics, where standard non-relativistic makes clear predictions. There are some situations where you actually don't even know how to use the standard apparatus, but where this theory you do know how to use it. But where in the non-relativistic regime, it makes exactly the same predictions. So you can't look at an experiment. There never has been an experiment that somebody could point to that experiment and say, oh, that experiment shows that this theory is wrong. If it did, it would, in a normal sense, show that quantum mechanics is wrong.
Okay. Any experiment that you know people did with proton?
And experimentalists have a kind of game, which is, what's the biggest object that we can actually see interference with? And they've gotten much bigger than a proton. They've done it with so-called buckyballs, which are these kind of soccer ball shaped complex molecules with many, many, many protons and neutrons in them. And they've seen interference effects of this sort from those. And they keep getting bigger and bigger. And the theory doesn't suggest there's any limit at all to how big an object should show these interference effects. It's just they get harder and harder to see. Intuitively, the larger the object is, the smaller the wavelength is, and the more difficult it is to see the interference. But there's no limit at all where it gets cut off completely. So this wave particle, duality, what people say, has been shown. Well, it's been shown for light, which originally was really thought just to be a wave, but this was the photoelectric effect that I talked about that Einstein worries about. So it shows behavior both that you'd associate with a wave and with a particle, and for electrons and protons, and up now to very large molecules, and they're trying to get bigger and bigger. So there's no indication that this doesn't hold for all matter. Everything we think of as matter has both of these aspects.
So that means everything has both particle and wave nature, rather, because the way we grow up, like when we are children, we see particle and we see discreteness. We don't see the wave part. Right. So as an adult, we cannot intuit that what can be a dual wave and particle in real life. So we don't have a physical representation. So that's why it's very difficult to fathom what the wave particle duality actually represents in reality.
It's true. In everyday life, you have objects like baseballs that act sort of completely like particles as far as you can tell, and things like water waves that just are wavy and don't seem particle-like. And so we don't have a good everyday thing. A lot of people got become very excited about these experiments that a guy named Coudray and some people did with these bouncing oil drops. So they would have a pan of oil on a device that was vibrating it, so there were little waves, and then they drop a drop of oil, and it turns out these oil drops bounce. Yeah, and as they bounce, they kind of walk around. So in a way, they're behaving, the drop is behaving like a particle, but where it goes depends on how it hits the oil bath and what the wave pattern is there. And they create their own waves. And so that bouncing oil drop thing has kind of particle-like and wave-like aspects to it. And so some people have thought, oh, this now helps me understand. It's it's kind of a visual thing. It's not so great for the pilot wave theory, because in the oil drop, it's really bouncing like this. And in the pilot wave theory, you have a particle and it's just being guided by a wave.
Continuous steering rather than bumping.
Yeah, it's not doing anything like that. It's moving in a nice, smooth way. It's just, that's why David Bohm, who developed this theory, called it the pilot wave theory. The point of the wave-like thing is to guide the particles, is to, as it were, determine where they go.
Now,
And if you're being guided by a wave and you are a particle, you can see how that would have both particle and wave behavior associated with it.
Who's the pilot here? The wave or
the wave is the pilot.
Exactly. Okay.
The wave is piloting the particle, and not pushing it around. That is, he's not piloting it by in a Newtonian way, shoving it. Sometimes Bohm would give you, if you want something to think about, suppose I have a radio-controlled boat. So the boat's way out there, and it's moving around, and as I turn the dials on my controls, the boat goes different ways. And you say, well, what's really guiding the boat? And you say, well, it's these electromagnetic waves that are coming from my controller. But the electromagnetic waves aren't pushing the boat around, right? It's not like so much force is going, the boat, it's what's really being sent, as Bohm would say, is information. In a way, the wave part is kind of informational, rather than forceful. It's telling it what to do or guiding it. So that's not a bad picture to have in your head.
Okay, yeah, that's a nice summary, because most of the time people stop thinking after seeing the wave and particle duality, but you also dissected a little bit more that it might be both simultaneously, not at a time. So this time is a wave, next time it is not a particle, is a particle. Actually, all the time it's both particle and wave.
And that is a confusion, because early on, Bohr especially would say things like, well, whether it's a wave or a particle depends on the experimental situation. So I can set up an experiment where it'll, as it were, behave like a particle, or set up a different experiment, and it has to be a different experiment where it'll behave like a wave. But just the two-slit example is one where you have one experiment and the outcome has both particle and wave, as it were, aspects to it at the same time. I didn't have to change the experimental apparatus. So it's not like I can force it to do this or I can force it to do that. It's like, no, it's both all the time. Yeah.
In Newtonian mechanics, if I see a particle A in position 1 and particle B in position 2, and I can continue to follow, I can predict where the particle will go, because I can observe the particle in a discrete position. But the quantum mechanics, because the particle is no longer a point rather than a wave function until you measure it, then everything the Newtonian mechanics do is not applicable for like micro world. So is there any reconciliation that you can think in future can unite this? Because Newtonian mechanics is obviously valid for almost all practical purpose.
Well, so let me just say, in this, again, I'm going to come back to this pilot wave. In the pilot wave picture, what you're saying isn't true. The particle is treated as a point. It's always a point. It's always somewhere. It has a definite trajectory. And in fact, the way David Bohm presented the theory, it's not my favorite way to present it, for reasons we could go into. But the way he presented it was using Newtonian mechanics.
Okay.
And what he did was he used the fundamental equations of Newtonian mechanics, F equals ma, and added what he called a quantum potential. So just as you have an electromagnetic potential or a gravitational potential that you're already used to in Newtonian mechanics, he said, oh, I'm going to use all that same apparatus, but add a quantum potential, and the quantum potential depended on the wave function. And in that picture, it's not only not contrary to Newtonian mechanics, it is Newtonian mechanics.
So that means
Now,
in that view is still a little bit more deterministic than the
it's
traditional.
completely deterministic theory.
Okay,
It,
that makes
it
sense.
wouldn't have to be, but it turns out that theory is completely deterministic. So in that theory, the only reason we can't predict exactly what will happen in an experiment
Mhm.
is that we can't get precise enough information about the initial state of the system. And there's an explanation for why we can't get that information, because the way you get information is by interacting. It's itself physical.
Mhm.
And so if you apply the theory itself, it tells you you can never know everything you need to know about the system by any physical interaction.
Mhm. Mhm.
So the theory says it's all deterministic, and it also says you'll never be able to make perfect predictions.
So results are probabilistic because you are not sure about the initial condition.
Exactly. That's right.
So now tell me, where does the Bell theorem comes in
Yeah.
this picture?
Good. So John Bell, when he learned quantum mechanics in just a normal way when he was a student, was very puzzled by it. And he didn't really understand it for reasons that anybody who's tried to learn it will understand. That, again, you're given some equations and you're told how to manipulate them, but you're not really given a physical account of what's going on. And he wondered, well, why can't I just think of the particles, the sort of thing we've been talking about? Why can't I think of electrons just as particles and they're moving around and in a much more Newtonian way? And he was told, oh, well, we know you can't because of a theorem, a mathematical theorem that John von Neumann proved. And people reported that this theorem showed that you can't, it was exactly this question that Einstein had raised. Is the quantum wave function a complete description of the system? And people said that von Neumann had proved it must be, that if you try to add anything in addition to the wave function, the theory can't make the same predictions. And so Bell heard this and he said, oh, well, I don't, he said, oh, he put it out of his mind. He said, well, apparently von Neumann has proven you can't do this thing. Now, what happened, what Bell reports is in 1952, he read Bohm's papers. They were published, and Bohm lays out this deterministic theory, this pilot wave theory, and proves it makes the same predictions as standard quantum mechanics. And so Bell was very puzzled at that point. And he said, wait, I thought von Neumann proved you can't do this.
Mhm.
And here I have in front of me, Bohm just did it. Now, what Bell reports is that when he was first told of von Neumann's result, von Neumann's book had not been translated into English, and he, Bell, didn't know German. So he had no way to really check what exactly von Neumann had done. But then when he read Bohm's paper, he did get hold of an English translation of von Neumann. And he looked at the proof and he said, there's an assumption in the proof which is unrealistic, but there's no justification for it, right? In a later interview, von Neumann said that the assumption is not only wrong, it's foolish. He didn't understand why von Neumann would ever think he was justified in making that assumption. And that the proof really didn't prove at all that you can't add things to the quantum mechanical description. And Bohm showed that you can. That's what got Bell started on this. Now, here's the key. If you look at Bohm's theory, and now you have this very clear theory, it says, okay, there are these particles, they move around, they're guided by the wave function in a certain way. Here's the equations. It's obvious when you look at those equations that this is a non-local theory, meaning if I can have a pair of experiments done very far apart, arbitrarily far apart, on a pair of particles that have been prepared in a certain way, and the outcome of one of the experiments can depend on how the other experiment is done. Okay, so Alice is 100 million miles away from Bob, but according to this theory, if I do it right, the result that Bob sees in his lab can depend on which experiment Alice does in her lab, arbitrarily far away and instantaneously. Now, this was the very thing that Einstein worried about. That's what he didn't like about quantum mechanics. Einstein famously called this spooky action at a distance. That according to quantum mechanics, an experiment done in one location can have a physical effect arbitrarily far away and instantaneously.
And those effects are always pertaining to a entangled pair, right? Not
Yes.
not regular. Okay. I have
That's
a
right.
question
In order
actually,
to
just
get
for
this, the two particles I'm experimenting on have to be entangled.
entangled.
But this is where entanglement comes
Yeah,
in.
exactly. That
That's-
concept, I have my question just for my clarification. So is it a definitional entanglement, or is it a physical entanglement? What I mean by that, for example, if you have a pair of shoe
Mhm,
and you know that you gave Bob a left pair, and
mhm.
for example, you can do a double blind, for example,
Yeah.
experimental, exactly, doesn't know which way
Yeah.
it goes.
Right.
But now they are galaxy apart, and because you know it was a definitionally attached, because right pair, left pair is a like analytic truth that
Right.
the two set has to be two.
Yeah.
So is the entanglement that you talk about with particles, they have similar definitional structure, or is something physical entanglement? It doesn't depend on definition.
Yeah, that's the perfect question. All right. So that question is exactly the question you want to ask. And the answer is, it is not like a pair of shoes. It can't be like a pair of shoes. That's what Bell proved. That's the heart of Bell's proof, was that you get correlations between the outcomes of these distance experiments that it is mathematically impossible to explain on the right shoe, left shoe model, where the shoes are always one's right and one's left, and one goes to one lab, one goes to Alice and one goes to Bob. Maybe we don't know, maybe nobody knows which went to who. What Bell proved, the very heart of what he proved, is that model can't give you these predictions.
Okay.
They can't do something, they can't violate what's called Bell's inequality, which is a very specific restraint on observed statistics and correlations between the two sides. They cannot be explained. That's why Bell's theorem is so important. It tells you this non-locality is physical. It's not definitional.
Okay. So it's worse
That's
than I thought.
And that's why we call it the John Bell Institute for the Foundations of Physics, because this is the most important discovery, arguably, in the history of physics. And it is the content of Bell's theorem.
Yeah, can you explain on a little bit what you mean by inequality part of Bell's inequality for general audience? For example, just give a simple illustration.
Right. So again, let's go back to let's imagine you think the world is completely local in Bell's sense. What does that mean? That means Alice has her lab in one location. Bob has his lab very far away, and they're doing experiments at the same time. Okay. In a local theory, you should have a physical description of what's going on in Alice's lab that makes no reference at all to Bob, and a physical description of what's going on in Bob's lab that makes no reference at all to Alice. And from those individual descriptions, you would make predictions about the outcomes in the two labs. Okay. Any such theory, if you start looking at the outcomes in these two labs, you can also look for correlations between them. That is, you can ask, okay, Alice is getting a certain kind of outcome, let's call it up, either up or down. And Bob is getting a certain kind of outcome, let's call it up or down. And then you can ask, does knowing that Alice got a certain outcome up, does that allow me to predict better what will happen to Bob?
In theory, there will be no prediction because they're independent events.
Generally, there'll be no correlation. If there's no correlation between them, knowing what happens to Alice will not improve my situation with respect to Bob or vice versa, right? So think of it that way. So in a local theory, that's exactly the way a local theory would work. Now, what Bell proved was that if a theory is local in that sense, that what Alice does has no influence on Bob, what Bob does has no influence on Alice, then he proved an inequality, which is just an inequality in the mathematical sense. It says this number plus this number is always less than or equal to this number. Okay, so it's the less than or equal to, the fact that it's less than, it's an inequality. So what he proved is that in a local theory, you could say, all right, if you set up various experiments that Alice and Bob are doing, and you just look at the statistics, this number plus this number would always have to be less than or equal to, or greater than or equal to this number. Okay, that's or this number plus this number has to be less than 2. Or the square root of 2. I mean, there are different ways you can set this up, but it's an inequality just because it doesn't say this has to equal that. It can't be greater than that. There's a bound. And so what Bell proves is that for certain experiments, there is this bound of what you can see. I mean, in fact, in the original one, there are 4 numbers that you set up that you can do experiments to calculate, to observe each of these 4 numbers. They have to be different experiments, but you observe each of these 4 numbers, then you add them up in a certain way, and Bell says that has to be less than 2. But in fact, when you do the experiments, it's more, I mean, according to quantum mechanics, it can be greater than 2, and when you do the experiments, it's greater than 2. And not even close, right? So you violated Bell's inequality, because if the theory is local, the number can't get that big. And it does, right? It gets much bigger. So, maybe the bound is 2, and what you observe is 2 root 2, or about, 2.8.
Yeah, let me try to understand, because if a theory is local, then our mathematics and statistics gives us some inequality. That means this experiment is double the size of that experiment, something like that. But if that inequality is broken, it is almost like saying 2 apple is greater than 2 apple.
Well,
actually, 3 apple should be greater than 2 apple, something like that. It's like mathematical violation.
The first part of it was exactly right. The theorem says if the physics is local, then this certain number that I can just observe, I can go into labs and observe these numbers and add them up. What I get when I add them up should be less than or equal to 2. If the theory is local, that number should be less than or equal to 2. I go into the labs, I get the numbers, I add them up, and it's greater than 2. Now, what follows from that? Well, that's just the standard thing. The theorem says if it's local, it won't be. It is, therefore, the physics can't be local, right? Then you just say, I've proven, I haven't told you how the physics works, but I know however it works, it must not be local. It can't be local. It must have in it somewhere this spooky action at a distance. It must have in it the very thing Einstein didn't like, the very thing Einstein objected to in quantum theory. And it's those experiments that just got the Nobel Prize, right? It was those experiments.
So after almost 50 years, this result has to wait for almost 60 years.
That's right.
So the spooky action, the Bell's theorem, to me looks like it is giving us a 2 blow. 1 blow against locality argument, because that's a commonly held scientific consensus that science works as if local, because if it is non-local, then a lot of things will break down, even some statistical results that you just mentioned, that ideally, based on our mathematics, it should be less than 2, but based on observation, it is more than 2. So it cannot be local, something like that. Right. So that's a blow against commonly held scientific consensus. The other one is the spooky action. That means if you accept the Bell theorem is correct, it is proven already, that indirectly means that the Einstein's hard cap on speed of things also getting violated. Like,
Yeah, I mean,
can you comment on that?
I understand. I mean, it's not exactly that there are two things, because it's really one thing. It's that Bell shows certain phenomena cannot happen if the physics is local, and those phenomena do happen. So it tells you the world, the physics, the actual physics of the world isn't local in Bell's sense. There is non-locality. This non-locality, he shows, it's built into quantum mechanics just in its predictions, right? That you're not going to suddenly find a different way to think about quantum mechanics where the non-locality goes away. That's what Einstein was hoping for.
Exactly.
And Bell says, sorry, Einstein, it's not going to work out, because the non-locality can be proven just by straight observation and a little bit of algebra without even mentioning quantum mechanics. Now, you come to the second point you made, which is connected to the first. Is this non-locality, does it also show there's something wrong with relativity? Right? Does it contradict the theory of relativity?
Mm-hmm.
Now we have another question. Well, what exactly does the theory of relativity say? People often suggest that it says nothing goes faster than light or something like that. And then you'd say, but the non-locality kind of requires information at least to go faster than light. The problem is that if you just look at relativity, it doesn't mention the word information. The way you form it, now you have to look a little bit deeply into what exactly the theory of relativity says. That was kind of the topic of my first book, which was called Quantum Non-Locality and Relativity. And it was just the first chapters are on what Bell did, and then the rest of the chapters are on, but what exactly does relativity, if anything, what does it forbid from going faster than light?
Mm-hmm.
And it turns out it's not so obvious. I mean, even before all this, for example, people argued that theoretically you could have particles called tachyons,
Mm-hmm.
which would just go faster than light, but nonetheless, you could do that in a relativistic way, right? It was consistent with relativity that there be tachyons. Now you just have to have another discussion. Well, what exactly is the theory of relativity, right? What does it assert? As I understand it, it itself is a claim about space-time structure, but it's not about information or anything like that. But what exactly it means to be precisely consistent with relativity or to be a relativistic theory, this requires, again, an entirely new foundational discussion. There's certainly at least a tension. Well, I mean, everybody sees there's a tension between relativity and this result.
Exactly. So I saw the two tension, like one is the commonly held scientific belief that mathematics and statistics and empirical data is good enough to predict the nature of reality, but if it is non-local in quantum world, this approach will not work. So that's one blow. The second blow is still indirectly to the relativity, because that puts a hard cap on how much, how fast you can communicate, or information can travel, or information can convey it, whatever you mean by that.
Right.
Exactly.
And I mean, let me just actually, again, connect your 2 points. Einstein very clearly stated this locality principle. This was before Bell, of course, in a letter. And it was exactly that. He's saying, look, I think the physical state of affairs in one location you must be able to specify it independently. There must be a physical state of affairs there that's completely independent of what's going on elsewhere.
Mm-hmm.
And Einstein said, if that weren't true, I don't see how we could make any predictions, because the thought in the back of his head was, to make a prediction for what's going to happen in my lab, I have to know what's going on everywhere. If you don't have locality, and we don't know what's going on everywhere, so how could you even have physics?
Mm-hmm.
Now, it turns out quantum mechanics is just a counterexample to that, because it is a non-local theory, but it does allow you to make these predictions, right? We know how to make predictions using the theory. So it's not that the non-locality automatically kills the ability to use the theory, and quantum mechanics illustrates that. The second point is, and now I'm going to say something that's extremely controversial. So,
I love that.
a warning sign. Okay, one's immediate thought is, gee, if there's this non-locality, if what Alice is doing has a physical effect on Bob, or vice versa, and has to be faster than light, why can't I send signals? Right? I mean, your immediate thought is, if there's this physical connection between them, why can't I somehow harness it or use it and allow Alice to signal to Bob? And if you could do that, then there would definitely have to be something wrong with relativity. Something would really be the practical ability to signal would make this into an immediate complete crisis. Okay. There was a point back when I was learning this stuff when people talked about peaceful coexistence between relativity and quantum theory on the model of peaceful coexistence between, the United States and the Soviet Union, that, oh, well, they kind of are in tension, but they can live together somehow. But if there was superluminal signaling, there couldn't be peaceful coexistence. Okay, then you're at the end of that. Now, there are some very recent results using this pilot wave theory that suggest that, yes, you can send signals faster than light, and suggest how you can do it. And to me, now it would be a very subtle thing to do. The experiments would be difficult. The signal would not be very strong. It would be a very weak signal, but you could do it. To me, this makes more sense. That is, to me, it's more surprising if there's non-locality and somehow you just can't signal with it.
Exactly.
Than if there's non-locality and you can, but it's hard, right? It's not something you're going to just stumble across fiddling around in the lab, right? You have to do some very, very precise setup and know what you're looking for, right? And know exactly what to do to see it. To me, that seems much more plausible. And we actually have a model for how that might work, involving experiments on entangled particles. But that's very, very controversial. And the work is just being the mathematics, and the work is being done now. I think it's really interesting. And to me, it doesn't shock me. It's the other way around. I'm kind of shocked by someone saying, no, this non-locality is there, but it's forever hidden from us in a certain kind of practical way.
Okay, I think for Bell's theory, we have enough introduction, but we have so many topics to cover. Let's move to another one, related topics, and then we'll move to time, because I really wanted to talk with you about time. So because this relativity theory, because they're trying to unify with quantum theory, the main obstacle I can see that in general theory of relativity, space is treated as, in Einstein's model, as a continuous variable, because space in Einstein's mind is indivisible all the way down, no matter how much you go in his mind. And similarly, in time, I don't think Einstein ever thought that time is also discrete. He felt time is also continuous. So if the space and time in Einstein's theory is analog or continuous, and the quantum theory says everything has to be quantized, otherwise our understanding of quantum physics is not right, but we already know that almost all prediction of quantum physics is correct. So there's a big clash. So is there any hope in our lifetime that you can see those will be unified? The point is, if these two different theories can be unified, somebody has to be wrong, especially Einstein. Because quantum theory has more experimental validity, right?
Right. I mean, let me make again. This is the the position you just presented is widely presented, okay? Absolutely widely presented. In quantum mechanics, whether or not something is continuous or discrete, it's not immediately decided it must be discrete. It's true that in relativity, everything really is continuous. There's no discretization of anything, of any quantity, that it can only take certain values and no values in between. So sure, everybody understands there is a tension. Again, the kind of mathematics you use to write down general relativity is just not the same mathematics that you use to do quantum theory, and putting them together or finding a single mathematical formalism, which would give you, as it were, what everybody wants, would give you something like relativity, general relativity, when you idealize in one way, and something like quantum mechanics, right? That both of them would be sitting inside this one theory. Nobody knows how to do it. This is what they've been looking for, a so-called theory of everything, for again over half, for over half a century. This has been the main thing that a theoretical physicist wanted to find, is a way to put quantum theory and relativity together coherently. People thought they had found it with string theory, but the prospects for string theory are not looking too good. It's not as easy as saying it's obviously impossible. Of course, something's got to give. Probably, if there is a single theory, and there has to be because there's a single world, that theory may involve adjustments, adjustments on the relativistic side and adjustments on the quantum mechanical side. It may be that, it's some third thing.
So in your opinion, the third, unified theory will be leaning towards which spectrum? More towards continuous relativistic versus more towards, or it will be right in the middle?
I think, what do I want to say? The final thing you want to talk about, I'll just say a word about here, which is this thing I'm working on. Really, maybe it's easier to just focus on that for a second. So it is a theory where in space and time everything is discrete. So the space-time really is discrete. So from that point of view, it's giving up that part of relativity, of general relativity, the continuous part. But there's still things in relativity that you sort of see there, like light cone structure, and so various aspects or surprising things in relativity that you didn't have in Newton, they're still there, but in a kind of discretized version. So you don't give it all. I mean, there's certainly recognizably relativistic structure
Will be there,
but modified in a certain way, right? Not as it shows up exactly in relativity. Yeah,
that makes sense. But let's hope we'll see it so that we'll appreciate, because that's the purpose of our podcast. I just wanted to know from the experts. Okay, now let's switch to completely different topics. So far, we covered the clash between quantum physics. What is it? What is the difficulty? What did Bell do? Then context with relativity, then pilot wave theory, a lot of things we covered. And it's counterintuitive, but that's the way the world works as far we can measure. But about time, people have so many different opinions, and commonsensically, we can appreciate that what happens in the past cannot be antecedent to the future, but vice versa is also true at the same time. Because if you say the cause and effect, that core, because most of the time we don't agree on a lot of things, but at least one thing everybody agrees in physical society or philosophical society, that cause and effect, those are commonsensical thing we have to accept, that things have cause and the cause always happens before the effect.
Yes.
So now, if you don't agree upon this timestamp that something happened before something else, so if you can reverse the entire course, then all the logical talking, all the logical argument goes out of the window because things become illogical. So that's why I am inclination, my common sense is time has some intrinsic property that you cannot violate. But if you read physics, especially relativity, especially quantum physics, there's no directionality of time inbuilt into it because they say time can flow forwards, backwards, you can contract, dilate, you can past can go. For example, I can, in theory, can kill my grandfather. It will create a separate universe to reconcile the difference. So all kinds of things, right? So what's your, like, for a general audience, what's your take on time's intrinsic property? Can be time secondary? Is time emergent rather than in something that you cannot, for example, something is irreducible versus something is emergent. So in your opinion, is time emergent or something irreducible? Let's start with that.
Look, I'm not sure if I'm going to please you or disappoint you with this answer. I agree with common sense and everything you said in common sense. I don't think there's anything in physics that suggests it's wrong. I think time is fundamental, it's not emergent, and I think it's directed. I think there's a difference between that some events precede other events, and that never goes around in a circle. It's not that anything precedes itself. It's not that, you know, my grandfather's life preceded mine. I mean, his youth preceded my existence, and that because of cause and effect, as you say, absolutely nothing I do can or could ever have any causal influence on my grandfather's youth. And you know, I'm sorry for people who like time travel stories and Back to the Future and all that stuff. I don't think that's physically possible. And I don't think there's anything in physics that suggests it's physically possible. I think there's a lot of very undisciplined, loose talk. And especially people who say, oh, time doesn't have a direction, because the reasons that they suggest they're saying that for would equally be reasons for Newton. I mean, let's at least be clear about this. If they were good arguments, they would apply to Newtonian physics just as well. So it certainly would not be some discovery of relativity or discovery of quantum mechanics or discovery of some, you know, string theory. But the fact is, the reasons they give aren't good reasons. And physicists, like everybody else, always implicitly assume and represent a direction of time, that some things precede others and that the causes precede the effects. And it's just the reason that this gets lost a little is that it's the conventions we use to represent time are so ingrained that we don't notice them. For example, if I have a number that's supposed to represent time, and that number is, you know, I have okay, there's 6 and then 7 and then 8. The idea is that as the numbers get bigger, that's the forward direction of time. All right. That's just the convention. It's a convention. We break that convention when we send off rocket ships, right? When we count down to a rocket launch, we go 10, 9, 8, 7, 6. And as the numbers get smaller, the time goes forward, right? But in almost everyday life, in all our clocks and everything else, it's just a convention, the way we assign these numbers, that the forward direction of time, the direction into the future, is the direction in which these numbers get bigger. So we know what direction time is going in, and therefore we know what could be a cause and what would have to be a cause and what would have to be an effect. And we use that all the time in our reasoning, and we use that in drawing our scientific conclusions. We use that in making our causal models. Everybody does. Physicists do, all scientists do. And there's no reason in the world to think that isn't true.
Yeah, you mentioned something, hidden assumption of time almost all theory already has, but later they don't acknowledge that they had the time assumption, and they can say things can flip. But if you dig deeper, if you see, oh, at the very bottom there's a time assumption already. I'll just share one of my idea. For example, the geometry. I think you are very keen with geometry. I'm just amateur, just sometimes play around with numbers and points. For example, if you create an x-axis, in order to create an axis to like one-dimensional line, you have to go from A to B, and B is not A. So for A to go to B, you already need time there. So time is already inbuilt prior I can build anything. So in that logic, commonsensical logic, I'm saying that time is in the bottom, whatever we built on top of it. Even space, in my like this commonsensical thing, that for example, in order to visualize a space, I have to imagine a dot. So the dot was not present. Now I am imagining. So that distance, that's a mental movement or imagination. That takes time.
Yeah, I mean, let me just, the thing about the axis, I understand what you're saying, which is to suggest that when you draw a line,
yeah,
you know, literally to draw a line, it's something that happens in time. You start at one end, and you know, if you're doing Euclidean geometry, you put down your straight edge and you draw, you draw a line. That's of course true. It's not the only way to make an x-axis, right? I mean, I could just take a ruler and dip it in ink and then just stamp, right, the whole x-axis instantaneously, without there being a sequential thing in time. So it's not, I mean, time isn't built into spatial structure fundamentally in that way. It's true that, of course, most of the things we do, and of course, all of our thoughts unfold in time, right? So our thinking unfolds in time. The idea of spatial geometry, just as a subject, is that it's not something that requires reference to time in the subject. Certainly, if you do Euclidean geometry, right, if you do Euclidean geometry, you talk about triangles and circles and their relations, and you know, and so on. And none of those concepts involves time. It's true that to actually do the drawings and to run through the proofs requires time. But what the proofs are about is, as it were, a purely spatial structure. It doesn't have to have any time aspect to it. Now, the world, of course, has a time aspect to it. So pure geometry, pure spatial geometry can't be all of physics. Physics needs to come to terms with time. And as you say, someone might say, well, I think time is somehow not fundamental. It emerges from something else. I think time is fundamental and other things emerge from it. And I don't even understand exactly how this other kind of emergence is supposed to work. And nobody's been able to explain it to me in a way that I even understand what the proposal is. Doesn't mean someone might not tomorrow explain it, but I've never heard anything I can wrap my head around, even what they're claiming. So yeah, I think time is a temporal structure is fundamental. It doesn't derive from anything else.
It's very comforting for general audience, because most of the confusion for any educated adult comes because they are already indoctrinated with the time's primacy. So now when they listen to different people, when everybody attacks time and causality and retrocausality, time travel, everything breaks down. So
Right.
I feel mentally dumbed down to pursue the.
I mean, let me go through an example I talk about a lot, maybe to make you feel a little better. Now, the time structure of the universe isn't what we naively take it to be. It isn't what Newton thought it was. I mean, I think you ought to be prepared to learn some things about time that do surprise you. And everybody is surprised by the so-called, when they learn relativity, the so-called twins paradox, right? So you have these two twins, and one just stays at home and the other gets in a rocket ship and goes off and comes back. And biologically, when they get back together, the traveling twin is younger than the twin who stayed at home. And Newton wouldn't ever expect that. Newton's theory of time wouldn't allow that. For Newton's theory of time, the same amount of time elapses between when they part from each other and when they get back together. There's just some amount of absolute time that elapses between those, and that's how much each one is older. So the twins paradox is certainly surprising. But the thing I like to point out is that it's not that surprising in the following sense. Here's an analog that everybody understands. I have two cars, and they start out together, and their odometers are set to zero, right? They're together, and their odometers read zero. And now they go on different paths. One takes the highway, and one takes a little, a side road, the scenic route. And then later they get back together, and now their odometers are no longer the same, right? They show different, as it were, elapsed.
One traveled more.
Right.
Yeah.
And you say, well, that's not paradoxical. They went along different routes, and what the odometer is measuring is the length of the route that they took from A to B. And they took different routes. No reason why they should have to be the same length. No reason why their odometers should still, even though they were synchronized at the beginning, should now be synchronized. That's all that's happening in the twins paradox. Clocks in relativity are like odometers. They're measuring something, and they're measuring something objective and real and physical. It's the length of the path through space-time. The way a clock functions according to relativity is it does measure something called the proper time. I mean, that's what it's called. The name of it is the proper time. And each of these two paths, if the twins start out together and then they take different paths and get back together, there's a certain proper time along those two paths, and they can be different. That's all. Just like there can be, the lengths of the paths when you're driving the cars can be different. And so the clocks show different amounts of elapsed time when they get back together. That's at one level surprising, but at the other, here I just gave you an analogy from everyday life where you'd say, okay, it doesn't surprise me about odometers.
Exactly.
I have to understand that clocks are not measuring the thing Newton believed in, which was this kind of absolute universal time. They're actually measuring something much more local.
Local, yeah. Okay.
Right.
In that sense, that completely makes sense. As a physician, I can give you another analog of exactly same thing. For example, two identical twins. One got adopted to a poor family, other got like aristocratic family. Now the poor people, like their living condition is bad, multiple infection, bad nutrition. They have to work so much. Like, Bangladesh, I am originally from Bangladesh. So we have a rickshaw pulling, like manually have to drive. So it's very energy intensive. So if you do those kind of work, and if you are malnourished, plus you have multiple rounds of infection, your body goes in catabolism, like your reaction, everything goes high frequency. So after 10 years, or maybe to be more visible, let's compare them 40 years of this aristocratic identical twin versus poor. So obviously the poor person will be aged like 60 years.
Right.
That doesn't mean they travel 60 years.
Yes, right, exactly.
So even in biological point of view, that odometer idea is very similar. So it doesn't violate common sense, but it also doesn't violate the time aspect of it.
Right.
Yeah, exactly.
I'm with the the man in the street, or the person in the street, with respect to the direction of time and the fundamentality of time. I think, as I say, time structure is not quite what Newton thought it was. I think it's closer to what Einstein thought it was, although I would suggest some slightly different, again, discretizing things. I mean, that's what I'm working on now. So I'm certainly willing to imagine that even Einstein, didn't get it all exactly right. But I don't think it's as radically, all of this radical retrocausation, grandfather paradox, creating new universes. I don't subscribe to any of that, and I don't think there is anything in physics that suggests it. Right? you understand why people are attracted to it. It's like science fiction, right? It's like so weird.
You can
And
overcome your death by time traveling. There's
yeah,
some movies,
exactly.
like Groundhog
Right.
Days. Groundhog
Exactly. I mean, all kinds of,
Days. It's
strange things. And I don't think there is any reason arising from physics to say any of that. I mean, I'll just mention something very quickly. This is slightly technical. There's a feature that a theory can have that's called time reversal invariance. That's
mouthful.
it's kind of easy to, well, it's easy to state mathematically what it means.
Okay.
And then physicists say, some will say, oh, if a theory is time reversal invariant, that shows that time doesn't have a direction. Now, there are two things I just want to comment about that. First of all, this feature Newton's theory has, right? I think calling it time reversal invariance is a bad name. It should be called time derivative reversal invariance. But I don't want to get into that. Anyway, whatever that feature is, that mathematical feature is Newton's mechanics has it. So if you thought it's not like relativity or quantum mechanics is somehow giving us this result. If you think that that's the result, it was already there. The second thing is, actually, quantum theory doesn't have it.
Okay.
This time reversal invariance. It actually breaks that. That was a very important. People got the Nobel Prize for proving that quantum theory is not time reversal invariant. It breaks what's called T-symmetry. So if you thought the reason for thinking time doesn't have a direction is time reversal invariance, A, that really doesn't follow from the condition, and B, the condition doesn't even hold.
Exactly.
So, I mean, I think there's a lot of stuff that's said about this that has no real defensible ground to it.
Yeah, exactly. So those who like formally accept that time can be reversible. For example, I saw interviews, and when they really hard press that exactly show me how, at the end nobody can show, rather it's just acceptance of a consensus, because that makes more sense based on the equation rather than a empirical data or example. So nobody can show that time reversibility is a reality rather than just a convenient way of describing the equation or something.
Right.
Something like that. Okay, so space, time, but now there's another elephant in the room, is the matter.
Yes.
So in your opinion, based on your study in physics and also philosophically, what is matter? Because it used to be called substance. So if you combine these two concepts together, so in your just share your idea, what exactly philosophical / physical matter that we call like minimum possible unit that you can do. For example, you used to call atom, right? But the atom theory broken down. But what gives the matterness versus the field? That's a difficult question, I understand, but I just wanted to hear from you.
Right. I mean, so there are two pieces to this question. Normally, what we think of as matter from the ancient Greeks when they were arguing about atomic theory or whether, and so on, we always think that matter is local. We've talked about non-locality. But you think, look, right here in space where my hand is, there's something here that makes it the case there's a hand here, right? The hand is made of something. And whatever that something is, it's right here. Yeah. So we think of matter as being local. So this is what, again, John Bell introduced this term, a beable, which is just anything that actually exists. And he says, among the things that physically exist, there are local beables, local things, and there could be non-local things. Now, the wave function that we talked about before, which I think must represent something physically real, doesn't represent anything local. It's a non-local beable. Let's call that the quantum state. Leave that aside. That's not what you're asking about here. You're asking about the local stuff. What is there locally that my hand is made out of? And there, from classical physics, we have two main possibilities that have been used. One is that it's particles, which means, little, I mean, you can think of them as little billiard balls or even point-like. They have definite locations at all times. They move through space and time in a continuous way. And the other is fields, like the electric field or the magnetic field, which are different in that they're spread out throughout space. They're spread out locally. You can ask locally, what's the electric field here? What's it here? But it's not that it's only at one point. It sort of is, a field occupies all of space at the same time, whereas a particle is only in one place. Now, what's anybody can see is that, first of all, the idea that matter is made of particles is very intuitive, and you can explain a lot of things in terms of it. There could be particles. This is what the pilot wave theory that I was talking about, the standard one, what the pilot wave pilots are particles, and they're really particles. They have locations, they move. But everybody can also see, suppose I had a field like the electric field, only it was almost 0, 0, 0, and then very high, that there were lumps in it. There was a field, but that it was often very, very low, and then at some points became very high. You can sort of see how those lumps of field moving around could behave like particles. So whether at base what's locally there in my hand, it could be, a countable number of particles, the way you think about there are a certain number of electrons, a certain number of maybe quarks to get below the level of protons and neutrons, but maybe quarks. That could be right. It could be that at bottom it's something a little bit more field-like, but where the fields get very clumped up, so that they kind of look like particles.
Yeah, I think
and I don't know. I mean, I think both of those are perfectly reasonable avenues to pursue.
Yeah, I think many philosophers, including Bertrand Russell, and I think physicists like David Bohm, they express, I don't know if they have written about it, but in the interview, I saw a couple of rare interviews of David Bohm. He mentioned exactly the same thing you mentioned, that matter that we locate as particle might be a concentrated region of the field.
Right.
So that indirectly gives the field is real, it's not just mathematical construct.
That's right.
Right, exactly. So,
and again, physicists have had this even apart from quantum physics. In electromagnetic theory of the late 19th century, you had electric fields and then you had electrically charged matter. So you had both fields and, like electron, and many physicists didn't kind of like that. Many of them thought, well, maybe I can think of the particles as just singularities in the fields, that really what there are the fields. And then when the field goes into a certain kind of special state, you get this local knot in it or something, which is what we call matter. And these ideas to me are it's not that one jumps out as more plausible than the other. All things that anybody ought to have in their toolkit, in their intellectual toolkit when they're doing physics. Well, maybe it could turn out this way, maybe it could turn out this way. There's nothing in the phenomena at the level that we can see things that decides that.
Yeah.
And it really should be, the tractability of the theory that decides which way.
You just mentioned about the knot. I think Lord Kelvin is a very old physicist. He had a very similar theory that matter might be a knot.
Yes.
They used to call ether at that time, the field.
Yes,
yeah.
Exactly.
So if you accept the field as a real, matter might be a degree of freedom restriction created by knots.
That's right.
So in that case, the particle wave duality can be reconciled a little bit, at least mentally. I don't know experimentally how can you do it, but at least it makes more intuitive sense to regard the matter as a continuation of the surrounding space. So
one could say, look, I think there are fields, and I think the fields are fundamental, and what we call particles are emergent in the sense that they are just special states of the field.
That's why I love you, because you have little bit of contrarian theory. Because most of the time, physicists don't say that field is primary, matter is secondary. They say either they're separate or matter is primary, the particle. Field is
Right.
just theoretical construct. That's a
Right.
dramatic difference, right? Don't you appreciate that?
Yes.
It's a dramatic difference. Yeah, exactly. Exactly. I love listening your podcast. I know in every podcast you say something as a reaction, and that makes me appreciate, oh, this is not just my speculation. It's in the literature. That's why you mentioned. So thank you for that.
But that's fine. But and let me say, I've said it several times, and it's true. The questions you're asking are the right ones. Okay. I mean, you are putting your finger where the real issues are. So that's, that's great. And I think you're right to be frustrated with some people who come out and make very extravagant claims. And at the end of the day, you can't quite see that they're backing them up. Because I think you're right about that too. Unfortunately, I think that happens a lot. If you're interested in physics, and you're interested in foundations of physics as a practical matter, that's not a good choice of a research field if you want to get a job in a physics department. It's just not. You're going to have a very much harder time. So the practical advice is, if you're interested in foundations, do it on the side. Try and keep an interest in it, but find something else to specialize in, where some physics department may actually be hiring in that field.
Like many people talk about plasma physics, that's the applied physics.
Sure.
Sometimes people talk about optical, like
Yeah,
laser physics.
And plasma physics is just the physics of plasmas, which is like, flames and so on, that things that aren't, it's neither solid, liquid, nor gas. It's too hot to even be a gas, right?
Exactly.
So plasma is a state of matter. Plasmas are very important. All this recent thing about fusion, the recent result in the fusion reactor, that's dealing with plasmas. So yeah, they're really important practical issues that come up in understanding plasmas and how they behave. The same thing for condensed matter physics, the same thing for, there are lots of subspecialties in
But those
physics.
are very close to the quantum physics, right? Plasma physics, condensed matter physics, rather than if somebody works in a mechanical engineering. That's also very commonly used engineering department.
Right. Mechanical engineering, you're really not going to do anything beyond Newton.
Yeah, exactly.
And of course, we know Newton's theory gives good predictions in a certain regime to a good approximation. We know that it's not good at a fundamental level. Like it could never explain the two-slit experiment, but an engineer doesn't care about the two-slit experiment. They just want their bridges to hold up, right?
Exactly.
And yeah, you'd mostly be learning just Newtonian physics for that. So I would be it would be irresponsible of me to offer any kind of blanket advice, especially because a lot depends on the goals. The advice that that many, myself and other people, have been giving young people who come to summer schools or come to conferences and are really interested in these foundational questions, and who have a background in physics and a background in mathematics. Sometimes we've been giving the result, well, maybe you should switch and get a degree in philosophy. Just as a practical matter, your chances of being employed by a philosophy department to pursue these questions are higher than you're being employed by a physics department or a math department to pursue these questions. And that's just the way things are. That's, as I say, because foundations of physics is not recognized in physics departments as a proper part of their field. Maybe in 10 years, in 20 years, it will be. And maybe in 20 years, the students who are really interested in foundations, like the students who are really interested in condensed matter, the students who are really interested in plasmas,
Exactly.
and just choose that. I'd like to do this. That's the end game, one hopes, of all of this. What would be great, what would be the greatest success for us is every summer to be a place where students interested could say, oh, look, there are, 4 or 5 different summer schools being offered in different topics with these experts who are being collected together from around the world because they're very dispersed, but you can really get a good, introduction to these things in a way that I can't get at my home institution because, in the physics department, nobody teaches this. That's the success we're hoping to achieve. We got set back by COVID, right? We sort of just we're starting, and we ran a couple summer schools in 2019, and then 2020 was COVID, and then everything was frozen.
Almost
We did a couple workshops
Mhm.
this last summer. Next summer we'll do some workshops and maybe some summer schools. The hope is to build up, but we're just barely surviving.
Yeah, I hope things will get better after this pandemic / economic depression, because also economy is pretty bad. But anyway, I think at least you started it. You set an example so that people can see that it's possible. As a philosopher, you can also do something outside conventional philosophy. Even the university doesn't support your research with money, like you're doing it on your own, this kind of research, right? Most of the problem is funding for project. And if your project doesn't have any practical utility, most of the time you don't get any fund. And that's the difficulty of this fundamental research, because there's no clear fund just to show that time is not real versus time is real. Who will fund it?
That's right.
Who will fund it? Yeah. Like the law we see in nature, it has a subjective component that we are not aware of, that you mentioned, that most physicists has a hidden bias or hidden assumption that is not said clearly. For example, like Newtonian physics is like habit formation. Like because you see repeatedly, you automatically assume, oh, that's the law and that's how it works. But the problem in quantum, we don't have physical representation. That's the, like I would say, the greatest hurdle to understand, because we cannot perceive it. But in order to perceive something, you have to have a starting point. And that starting point is your mind. And mind is an abstract concept again. Let's talk about the neurochemical circuitry to understand what's going on outside, sensory perception. So even that sensory perception starts with motion, some kind of motion. Without any motion, it's not theoretically possible, current neuroscientific term, to perceive anything. So now, if you talk about motion, it involves particle, because without particle, wave, unless they behave like peak, like summation, the motion part is gone. For example, if one wave cancels other, there's no motion. So particleness versus waveness, this kind of stuff fascinated me. That's why I was studying a little bit of, because I think the reason I was particularly interested in quantum physics, because they mention that our eye can perceive one single photon. That's pretty high sensitivity, right? Because if you imagine that eye is a macroscopic structure, and if you go outside, you cannot see anything in the night. But if you stay in the dark for longer, your eye picks up the stars that usually not visible. So the hidden assumption is always the self. And the self part involves time, because in order to say I exist, the moment you say I exist, time is already embedded in it, because existence linked with time. So that's why time fascinated me, wave versus matter fascinated me, and you are the master of those topics. So I'm so happy that I found you, at least talk about those things, so that I feel that I'm not off the chart. I'm just still within the domain of discussion that conventionally people do, that outsider typically are not aware of.
Yeah. I mean, let me just say that I don't want to get into, it's not my field, neuro. The first thing you were talking about, which is that physicists, as everybody, when you think about something, there are often assumptions you're making tacitly, right? That they're bounding the way you think and the possibilities you think there may be. And often these assumptions are ones you're not aware of. And when I said, to do this work well, you need some training in physics and some in math and some in philosophy. And a lot of the philosophical training, what philosophers do often is make these hidden assumptions manifest, right? Dig out what is the fundamental assumption, what are the assumptions of the way you're thinking about this that you're not aware of? Let's make them, bring them out into the daylight, examine them, imagine how maybe they could be wrong. Okay. And that's something that a philosophical training is very useful in helping people to do. And everybody ought to do that, right? Everybody should be aware that no matter how convincing an argument may sound, unless you look at it carefully, there could be assumptions that have gone into that argument that could be wrong and are misleading you, and you're not even aware of it because you're not aware you're making them. And of course, for physicists, it gets a bit worse, because what you would like to make manifest are the physical assumptions of the theory, right? What exactly does the theory assert? What does it say exists? For example, to use the example we've talked about a lot, if it says there are particles, then there are lots of questions that are immediately, reasonable to ask. Well, how do they move, and what are their trajectories, and so on? But physicists have often been actually positively dissuaded from asking exactly what the physical assumptions are. They're rather told, here are some equations, learn some math, learn how to calculate and get these predictions out of the equations, and don't ask what's really going on physically.
That's unfortunate, right?
And that's the result of quantum mechanics, and that's this so-called attitude called shut up and calculate. And that's what's killed foundations of physics in physics departments. It's not just neglect, it's homicide, right? I mean, a certain kind of curiosity is beaten out of the students. And it's a great tragedy, and it can be reversed. You just need enough people who are willing to reverse it.
Exactly. I hope that will come soon in our lifetime, so that we can see, and plus we can talk about your own research in our next episode. I will be in touch with you.